Advanced Algebra 2, Quadratics in Real Life. Let's go through some problems that are applications of quadratics. These problems are going to use all three forms of the quadratic equation. So vertex form, standard form, and intercept. With each different situation, you want to be heads up with what form is being used or what form you can use, and then figure out how to find what you want to find to answer the problem that's posed. So let's look at number 1, modeling with math. So flying fish use their pectoral fins like airplane wings to glide through the air. So A says write an equation of the form y equals a times x minus h squared plus k, and that's vertex form, with the vertex 33,5 that models the flight path, assuming the fish leaves the water at 0, 0. So let's capture that vertex form. And let's write down what we know. So at 33 feet out, that fish is 5 feet high, and it starts at the point 0, 0. So to write an equation, the only thing that we don't know is the a value. So let's plug in what we know to find a. So we're plugging in 0 and 0 for x and y, and 33 and 5 for h and k. Now let's solve for a. We'll divide by 1,089, so a is negative 5 over 1,089, and we don't want to round. We want to leave it in exact terms, so we'll leave it in fraction form. Now we can plug in that a value, and there we have it. There's the vertex form of a quadratic equation that models the flight path of that flying fish. What's the domain and range of the function? So normally we would say, oh, that's easy. It's all real numbers, and then we would look at the y value of the vertex. But this is a real life situation, and so x is the feet out that the fish is going to fly, so it has limitations. The fish will not go negative feet out of the water, and then the fish will not just go out, remain out of the water forever. So since we know that the vertex is at 33 feet, that is halfway through the flight path of the fish. So that means the full flight path is double that, is 66. So the domain ranges from 0 to 66. So the domain, right? The range is how high the fish can go. Well, we know that the maximum height will be at the vertex, which is 5 feet. So the range will go from 0 to 5, and that's the y value. C says, does the value of a change when the flight path has a vertex at 34? So this flying fish reaches a maximum height at 4 feet up, 30 feet out, and only travels a full path of 60. So yes, it does. And we can do the math to show that. So let's plug in 0, 0 for x and y, because this fish also starts at 0, 0, and then 34 for h and k. So our new a value simplified is negative 1 over 225. Number 2, the function f of t equals negative 16 t squared plus 10 models the height in feet of an object so many t seconds after it is dropped from a height of 10 feet on Earth. The same object dropped from the same height on the moon is modeled by negative 8/3 t squared plus 10, because it takes a different amount of time for something dropped at a certain height to reach the ground on the Earth than it does the moon. Describe the transformation of the graph f to g. So let's write both of those functions in front of us and take a look at them, see what's changed. So what I notice is the only value that has changed is the negative 8/3. So I'm thinking, what do I need to multiply negative 16 by to get negative 8/3? So we can work backwards to help us know what that transformation was. We can take negative 8/3 and divide by 16. Let's just work backwards to see what that multiply is. When you divide, you will get 1/6. So that means that just our x value there is being multiplied by 1/6. So we have a horizontal stretch by a factor of 6. That means that our multiplier is 6. 1/6. Now the next part of the question says, from what height must the object be dropped on the moon so it hits the ground at the same time on Earth? Well, we see that the moon A value has been transformed by multiplying by 1/6. So if we also multiply that 10 by 1/6, then we'll see the height adjusted. So 10 times 1/6 will give us approximately 1.67 feet. So something dropped on Earth at 10 feet and dropped simultaneously on the moon at 1.67 feet will fall and hit the ground at the same time. Number 3, a soccer player kicks a ball downfield. The height of the ball increases until it reaches a maximum height of 8 yards and 20 yards away from the player. So let's draw a little graph of that. Here's the first kick. So we have a maximum height of 8. So at 20 yards out, that ball hits the maximum height of 8 yards. Since that's halfway through the path, that means that the ball will land back on the ground after 40 yards. Let's look at the second kick. It's modeled by this equation, so let's capture that. Now our equation looks like it might be in intercept form, but it is not, because we need to have a coefficient of 1 in front of that x. So what we can do is multiply the x across that parentheses and rearrange our terms so that we have in standard form. We need to answer the question, which kick travels farther before hitting the ground, which kick travels higher? Well, if we find the vertex of the second kick, then we'll know maximum height and how far the ball traveled. So it looks like the ball traveled 25 feet to reach a maximum height of, and we're plugging in 25, of 5 feet. And so since 25 is halfway through the path, this ball's path, that means doubled the second kick traveled 50 yards, which is more than the first kick. It only traveled 40 yards. Which kick travels higher? Well, you can see that the first kick traveled 8 yards high, as opposed to the second one only 5 yards high. Number 4, although a football field appears to be flat, some are actually shaped like a very shallow parabola, so that rain runs off both sides. The cross-section of a field can be modeled by this equation, where x and y are measured in feet. What's the width of the field, and what is the maximum height of the surface of the field? So let's examine this equation. Now this equation is in intercept form, because see how I can open up a parentheses and put in a 0. So my first intercept is actually at 0, 0. My second one is at 160, 0. So we can think of it as our p-value is 0, that's one x-intercept, and our other x-intercept is 160. And then halfway would be 80, so that maximum width, so now we actually know what the width is. The width is right in front of us. It is 160 feet. Now to find the maximum height, that's whenever you see maximum or minimum with the quadratic, that means we're going to be looking at something with the vertex. So we'll find the x value of the vertex, and so that means that that maximum height of the field occurs 80 feet in, right in the middle. So we plug 80 in for x, and our y value is about 1.47 or 1.5 feet high. So it's just a slight rise, so that there's a very shallow parabolic shape, so that water will run off both sides of the field. Number 5, problem solving. So an online music store sells about 4,000 songs each day when it charges $1 per song. For each 5-cent increase in price, about 80 fewer songs per day are sold. Use the model to determine how much the store should charge per song to maximize daily revenue. So revenue equals the price per song times how many songs are sold. So R of X, that stands for revenue in terms of dollars, equals, so we know right now it's a $1 plus 5 cents per, we don't know how many increases, so we'll call that X, times our price. So it's 4,000, the sales. So it's 4,000 songs if the price is $1. But for each 5 cent increase, we need to subtract. So we can set up a little clever, this ends up being a quadratic. Now this is not quite an intercept form, so we're going to need to multiply this and rearrange in standard form. So then we can take a look at the vertex. So I'm foiling these two expressions, and then I'm rearranging. So negative 4x squared plus 120x plus 4,000. So now this is my equation in standard form that represents our revenue in terms of dollars for the number of increases. So we want to maximize that revenue, so we're going to focus on the vertex. Now this tells us that our revenue will be maximized after 15 songs. Or rather than 15 songs, it would actually be 15 increases of 5 cents each. Now we need to know the price, so we're not going to plug this 15 into the entire equation. We're just going to plug it into the first expression that will give us the price. So it's $1 plus 5 cents per the number of increases. So 15 increases, that's 75 cents. So if this music store sells their songs at $1.75 each rather than $1, they will actually maximize what they can make. An electronics store, kind of same thing, sells 70 GoPro video cameras per month at a price of $320 each. For each $20 decrease in price, about 5 more cameras per month are sold. Use the model to determine how much the store should charge per camera to maximize. So again, we've got an equation that we're going to multiply together so that it's in standard form, and then we're going to look at the vertex. So our X are our number of increases, or sorry, in this case, it's decreases in price, so $20 decreases. Now I'm rearranging this and combining like terms. So we're going to focus on the vertex. So let's find the X value of the vertex, which is how many decreases will maximize the revenue that the store can make. So just one decrease. So then to find the price, well, you can probably do that in your head. 320 minus 20 will be 300, but we'll do the math. So the store will maximize its revenue if they reduce the price of the video camera to $300. A woodland jumping mouse, and this is a real thing, hops along a parabolic path given by this equation, where x is the mouse's horizontal distance traveled in feet and y is the corresponding height. Can the mouse jump over a fence that is 3 feet high? So we need to know the maximum height that this mouse can jump. So we're going to focus on the vertex. Notice that this is in standard form. So let's find the x value of the vertex. And that will give you the height out, or, kind of horizontal distance in the mouse's jump where it reaches the most height. So at 3 1/4 feet out, the mouse is at its highest point. So let's plug in 3.25 for x, and we'll find out the maximum height that the mouse can jump. And sadly, it's only about 2.1 feet. So the mouse could not clear a 3 feet high fence. So see how each of these are different? Some are in standard form, some in vertex. Usually what we end up focusing on with all of them is the vertex. So let's look at this. A kernel of popcorn contains water that expands when the kernel is heated, causing it to pop. The equations below represent the popping volume in cubic centimeters per gram of popcorn with a moisture content of X. So we see hot air popping and hot oil popping. So for hot air popping, that's the top equation. What moisture content, so that's the X, maximizes popping value, so that's Y. And then what is the maximum value? So we want to know both parts of the vertex. These equations are in intercept form, so we're going to use what we know to find our vertex from intercept form. So we add our P and our Q values divided by 2, and hot air popping at 14.06% moisture will have maximum volume poppage. So now let's plug that into the equation, and we'll see how many cubic centimeters for hot air popping. So about 55.5 cubic centimeters. Now let's look at the hot oil popping. So let's take the P value, add it to the Q, divide by 2. So a little less percent moisture in the kernels. And now let's plug that into the hot oil popping, and let's see what the volume is maximized for hot oil. So only 44.1 cubic centimeters. All right, although I don't know about you, but I personally like the hot oil taste as opposed to hot air. And hot oil, so at this percent moisture, maximum value. All right, that concludes just some applications of quadratics.